All right, welcome to our first lesson in college algebra. It's our first day of the school year. I apologize for not being there. I will be back on Monday. We can consider this like the day after a unit exam. Typically on days after unit exams, we will go over the exam and then have a lesson. However, on every other class day, the structure will be going over problems, doing practice problems, then quizzing, and then starting in on the next lesson. So these are the few days where we will not have a quiz during class. Is this first day of school, first lesson, as well as days after unit tests. Okay, but every other day, remember, most of your 40% goes into your daily quizzes. You have your notes that you can write as much or as little on as you follow along through my notes. These videos that I record, I'll be recording every class period. They'll be posted at the end of the day, and you can re-watch lessons at the end of the class period or at the end of the day as a way to either finish the notes if we didn't get to everything, or to review the concepts before the quiz, the next class period. I recommend to work through the homework problems that are assigned. You do not have to do all of them, obviously. They are not going to be collected for the foreseeable future. Myself and Mr. Huffaker, the other college algebra teacher, may talk about using homeworks in the future if this new class structure is not working. But for right now, they're not going to be collected. But we would obviously advise you to practice and to either re-watch the video, do the problems from scratch yourself from the notes. A blank copy of the notes will be posted on the website, on the Schoology page. And there's also the homework problems out of the book, where the book pages are on the website. I can show you the website really quickly. I'll show you that at the end of the class. All right, so our first unit, really the first couple units that we are going to be talking about, most of college algebra is a review of Algebra 1 and Algebra 2. So, this is some severe review. We'll go all the way back to the first units in Algebra 1 with some of the stuff that we're doing today and the next class and the next class. Some of you may think this is incredibly boring or it's like a waste of your time, but it is so important to have these basic, solving equation and properties of addition and subtraction, fundamentals down. If you do not have these down, or if you did not have them down before, it'll be so important to strengthen them for you moving forward. We are just going to be solving equations by the end of this class period. If you already know or you think you're an expert, great. Hopefully you will learn something today, or at least you will, just quickly get back into, your top peak algebra form. And we're going to start with just simple things like addition and subtraction, addition of numbers. What's great about addition as opposed to subtraction is addition is commutative. 3 plus 5 in this order is 8. That's the same as 5 plus 3, 8. Addition holds what we call the commutative property, where if you have A plus B, it's the same as B plus A. I love addition. Whenever I can use addition, I will try to add things because I can't make a mistake. I don't love subtraction because if I do an A minus B and then I look at B minus A, I find that they are not the same. 3 minus 5 is negative 2, but 5 minus 3 is 2. So this is not the same, or not commutative. But there's a workaround to this. If I decide to change this from subtraction to addition, and I can, because subtraction is the same as adding the opposite. Okay, so if instead of making it a minus b, I make an a plus a negative b, well, I still get negative 2. But watch, if I flip-flop this, now that it's addition, this will be negative b plus a. That's negative 5 plus 3. I will get the same answer as I did before. So what I recommend to students is don't use subtraction. Instead, change subtraction into adding the opposite. And you will find that as I work through problems all year, I will prefer to use plus a minus or plus the opposite instead of staying with a minus sign. So for these two, before I even look at what's going on, I know that I want to change the subtraction to add the opposite, this to add the opposite. I just love doing it. It prevents mistakes. And in this situation, we deal with something with a variable, 3x and 5x and 3x and 5. And this is just to show you that you can only add like terms. We call this, I could call this like an apple. Well, this is an apple. If I have 3 apples, I can add negative 5 apples. Now I'm adding negative 5 apples. I'm taking away 5 apples from 3 apples. How many do I have? I have negative 2 apples. Okay, negative 2 x's, 3 x's, add negative 5 x's, I have 2 x's. But here, if I have 3 apples and then I have 5, well, 5, I don't have 5 apples. I just have the number 5. Or if I had like 5y, these would be like oranges. If you do not have like terms, you cannot add them together. So I would just leave 3x minus 5 as 3x minus 5, or 3x plus a negative 5. Okay, so can only combine your like terms. Okay, good start. Now, multiplication and division. Multiplication, also my friend, because if I multiply two things, a times b, or multiplying by b times a in an opposite order, multiplication will give you the same answer. 6 times 3 is the same as 3 times 6. So multiplication is my friend because it is commutative. However, division, 3 divided by 6, I can write it as a divided by b, or I could write it as like a over b. Okay, and this would be b divided by a, b over a. Division, not my friend. 3 divided by 6, which is the same as 3 over 6 or 3 over 6. This is equal to 1/2. We can simplify that, or if I type that into my calculator, I'd get 0.5. But if I have 6 divided by 3, which is 6 divided by 3 or 6 over 3, this is the same as 2. Okay? So, division, not commutative. But there's one way to change division so that we can use just multiplication, which is my friend. You will hear me often like to stick with things that are my friends, which is addition and multiplication, instead of using subtraction or division. Okay? And that deals with division being the same as a multiplicative, I don't want to say inverse, I want to rather say reciprocal. Turns out 3 divided by 6 is the same as if I take 3 and multiply by 1/6. 3 divided by 1/6 is the same as 3 times 6. Okay? Instead of dividing, you can multiply by the reciprocal. Now, what is a reciprocal? A reciprocal is when we take 1 and divide it by whatever number we have. So if it's like 6, it turns into 1 over 6. If it's 1/6, it's 1 divided by 1/6. Well, 1 divided by 1/6 ends up just being 6. So the reciprocal is actually what we can consider a flipped fraction. We should be aware that any number can be written as a fraction if you just take a 1 and put it underneath. 3 divided by 1 is 3. 6 divided by 1 is 6. So if I take 6 over 1, flip it, it becomes 1/6. 1 over 6 is already a fraction. Flip that, it becomes 6 over 1. That turns into 6. Okay, so this is the idea behind a multiplicative reciprocal. If I have 5 divided by 3, it's the same as 5 times 1/3. 5 divided by 1/3, the same as 5 times 3. Okay, instead of dividing by fractions, we can multiply by reciprocals. Or dividing by numbers, same as multiplying by a reciprocal. Now, speaking of fractions, we need to just remind ourselves how to work with fractions. It's important that we know that any number can be changed to look differently without changing its individualized properties. So like 2/3, I can decide to multiply this by a version of 1. And if I take a number and times it by 1, it stays at the same number. So 2/12 times 1, it's going to be 2/12. But 1 has an infinite amount of ways that we can make it appear. So instead of just writing 1, I could write 2 divided by 2. 2 divided by 2 is the same as 1. And if I wanted to, I can now multiply these two things together without changing my initial value. Now, we should recall multiplying with, by fractions is just we can multiply across. 2 over 3 times 2 over 2 can turn into 4 over 6. 4 over 6 is the same as 2/3. It just looks a little bit different. So here, 2 over 12, I can multiply by a version of 1, but instead of maybe multiplying by a bigger number, I could decide to multiply by a fraction or divide by a number. I can multiply by 1/2 over 1/2. 1/2 over 1/2 is the same as 1. So I'm not changing what this is, but I am going to make it look different. 2 times 1/2 ends up being 2 over 2. That's like 2 over 1 times 1 over 2, 2 over 2, which is 1. And then 12 times 1/2, 12 over 1 times 1 over 2, that's 12 over 2, that's 6. So all of a sudden I just took two different fractions, different looking fractions, and I just manipulate them by multiplying them by a version of 1. Multiplying by 1 does not change things. This helps us to be able to add fractions together. Okay, these are 2/3 plus 2/12. Well, unfortunately, these are not like terms. I have 2/3. I could rewrite it like this if I'd like to, 2/3. And this is 2/12. If I wanted to write it like this, I could. 2 times 1/3 and 2 times 1/12. Okay, well, 2/3 can't be added to 1/12. They're not like terms, but what we could do is manipulate these so that they are like terms. So they are apples to apples. And just like I did above, I can multiply this guy by 2 over 2, which is a version of 1. Multiply this guy by 1/2 over 1/2, which is a version of 1. It's the same as dividing by 2. I know you're probably thinking, why isn't he just dividing the top and bottom by 2? I am. I'm just making it look a little bit different so that I'm using multiplication instead of division. This turns into 4/6 like we have above. Hold on, having some technical difficulties. There we go. We have 4/6 plus 1/6. We now have like terms. 4/6 plus a 6 gives us 5/6. I'm going to use an equal sign here, however. We'll talk more about equal signs and their meaning moving forward. Okay, and just another reminder of multiplying fractions. We can multiply straight across. We do not have to have like terms when we have multiplying. Now, Again, why does this work? Well, because I could write this as 2 times 1/3 times 3 times 1/4. And I can have things in any order that I want to with multiplications. I can multiply the 2 and the 3 together. The 2 times the 3 is 6. I can multiply the 1/3 and the 1/4 together, giving me 1/12. I can multiply these two things together as well to give me 6/12. And if I'd like to multiply the top and bottom by 6, 1/6, I end up with an answer of 1/2. What we can see, because I can order these in any order, instead of multiplying the 2 and the 3 together, why don't I multiply the 3 and the 1/3 together? Multiplying the 3 and the 1/3 together gives me 1. Okay, and then I just have 2 times a 4th. Well, that's 2/4. That's another way to get to the 1/2. A lot of people know that, oh, I could have just canceled this and this to get 2/4, which simplifies to be 1/2. Why can you cancel it? Because of the property of multiplication, being able to first split this fraction into multiple parts, 2 1/3, 3 1/4, and then to be able to multiply the 1/3 and the 3 together before you do anything else. Okay, so I hope I'm not confusing you. I hope I'm just making sense and doing things maybe a little bit differently from how you're used to. You do not have to do things the way I do them, but it's important to know why certain things work or do not work. As we go into solving equations, you may have already developed the way that you do things, and that's great, but might be advantageous to see different ways to approach equations. But as long as you get the right answer, I'm going to be a happy teacher. Okay, just hopefully I'm opening your mind up a little bit about some things, not confusing you too much. 2/3 divided by 3/4. Instead of dividing, I know I can multiply by the reciprocal. I do not like to divide when I don't have to, and I never have to because I can always multiply by the reciprocal. Now it's the reciprocal of what we are dividing by 3/4, whatever's in the denominator, whatever comes second. That turns into 8/9 by multiplying 2 and the 4 and the 1/3 and the 1/3. Okay? Okay, great. Now, another important thing we need to remember is distribution. If I have 3 times 5 plus 2, I know that I could add 5 plus 2 together. If you remember order of operations, I'm going to remind you of order of operations in a second. And that becomes 7, and I can multiply 3 by 7 and get 21. Okay, and that's great. But instead, if you would like to multiply 3 by this entire quantity of 5 plus 2, you may do so long as you multiply 3 by the entire quantity, which means you need to multiply 3 by both the 5 and the 2, giving us an alternate form of this 15 plus 6. Well, if we notice, 5 plus 2, which is 7 times 3 is 21. 15 plus 6 is also 21. We get the same answer. I could have done things either way. However, let's say we want to simplify this, and this has a variable, and I want to get rid of these parentheses for whatever reason. Well, since I don't know what x is, I can't simplify the inside of the parentheses. I can't say what this is going to be, what this number is, because this is an unknown. Instead, what I can do is distribute and multiply 4 by this entire quantity. Now, watch what I do here. I have a minus sign in here. I don't like minus signs. They cause confusion. They create mistakes. I am instead going to change this into add the opposite. That way, I know this is a 4x. Since I changed anything, something from a subtraction to an addition, I know I'm going to have an addition. And I just have to worry about the sign of the next one, 4 times -2. Now, something we didn't go over, helpful reminder maybe next to the order of operations. Just remember, a positive times a positive is a positive. A positive times a negative is a negative. The same as a negative times a positive. That's also a negative. and a negative times a negative is a positive. Now, explaining why a negative times a negative is a positive or a positive times a negative is a negative is kind of difficult. What I like to think about is, canceling things out sometimes with negatives. Like when you're adding negatives, it removes some of the positives. Well, that canceling occurs, multiple times when we are multiplying. So that's some way to remember that or to understand that. But it is something that you need to definitely have known, that if you have a positive times a negative, it's a negative. Negative times a positive, it's a negative. And a negative times a negative is a negative. Okay, so this is the same for division as well. If we are dividing, the same rules hold. All right, now let's remind you of some order of operations. If I were to evaluate this, I would use the acronym PEMDAS. Now, what does PEMDAS stand for? You probably know. Stands for parentheses, then exponents, multiplication, division, addition, and subtraction. This is the order we'd like to work through things. So first thing you're probably thinking is like, okay, 3 times 1 plus 3, multiplication comes before addition, so I should multiply this first. And you would be wrong if you thought that could happen. I cannot multiply in this 3 into the 1 plus 3 because of this E, which stands for exponents. Can't multiply anything until the exponents have been removed. So if I were to evaluate this, I need to get rid of this square. Now you might be thinking, oh, let me square both the 1 plus the 3. It doesn't work like that, and we should know that, and we'll deal with that more when we get more into quadratics. Instead, we need to square the entire term, so we have to square 1 plus 3. So really, this is where parentheses come into play. If we have parentheses, let's work inside the parentheses first. And this turns into a 4 that's being squared. 4 squared is 16. It's 4 times 4. So this turns into 3 times 16 over 2. Now, here's an interesting thing when we have multiplication and a fraction. What can we do? Well, if you would like to, you can split this into just a bunch of different pieces. 3 times 16 times 1/2. And you realize you just have the multiplication of 3 different pieces. This, 1/2, not 1/12. This allows you to understand simplification and what you could do. I could decide to multiply the 16 and the 1/2 first. I can multiply anything in any order, one at a time. Well, the 16 times 1/2 is 8. That's 16 divided by 2. 8 is a half of 16. So it's almost the same as saying, oh, boom, boom, this turns into 8. And then I could do 8 times 3. 8 times 3 is 24. So it turns out this is 24. This all needs to be worked out without a calculator. We'll talk about calculators in this class. You will be able to use simple, like 5-function calculators, but it's important to not be able to rely on it when you get to college. Typical college math classes say no calculator at all. So if this is a college preparation course or a college algebra type course or something beyond that, like a pre-calculus course or a calculus course, you need to be comfortable doing it without a calculator. Okay, fantastic. So we got orders of operations down. We talked about addition, multiplication, subtraction, division. Let's talk about equality. Okay, equal signs are the most important things that you will see in algebra, stating that something is the same as something else. This creates a balancing act. We call equal signs balanced. Okay, think about a scale, where you have certain weight on one side and you have a certain weight that needs to match the weight on the other side. If you were to add anything onto one side, what would happen? the scale would tip, and we'd have one side that would go down and the other side would go up, making something unbalanced, okay? With equalities, you must keep things balanced. So if you were to add something on one side, for things to remain balanced or equal, you must add the same thing on the other side. Close enough. Okay? Now, if you multiply, say if I double what I have on the left side, I need to double what I have on the right side to keep the balancing act alive. Okay? This is important when solving equations. When we have an equation, we can add whatever we'd like to one half of the equation, so long as I add the same thing to the other half. We can then turn this into a 7 on the left side and a 7 on the right side. That's great. We could add the opposite, anything that we want to. All of a sudden, this turns into 3 is the same as 3. The balancing act still holds. I can multiply by anything. Let's say I want to multiply both sides by 2. Now, I can do it since multiplication works from left to right or right to left. I can put a times 2 on this side and a times 2 on that side. That's fine. 2 times 5 is the same as 5 times 2. This turns into 10 and this turns into 10. That's still balanced. That's great. Be careful with division. Division should either go underneath but do not put it on the side. Don't put like divided by 10, because if you read this is 10 divided by 5. 10 divided by 5 is 2. That's different than 5 divided by 10. So I don't like to put things on the sides when we're dividing because it messes up. This is why I don't like division, really, because it screws things up. 10 divided by 5, not the same as 5 divided by 10. But you can, instead of dividing by 10 and get 1/2 and 1/2, that's fine. You could, instead of dividing by 10, you can multiply by 1/10 on both sides like this. And we still have the balance because this is the same as that. Multiplication is our friend. We still have that balancing act. Now, two things that are really important, and sorry for writing all this stuff down, is removal of something. You know, if I want 5 to go away, I don't want it necessarily to go away, but watch what I can do. I can add the opposite. Always add the opposite, and 5 plus a negative 5 or 5 minus a 5 is a 0. So if I ever want to get rid of a 5 or make it a 0, remove it, I can add the opposite. Boom, I have 0 equals 0. Totally legal. Another thing we could do to essentially remove it, if I had a variable next to it, say I have an x and an x here, is multiply by a fifth or divide by 5. If I multiply by a fifth, or same as dividing by 5, 5 times a fifth is 1. I have 1x here and I have 1x here. Well, we know that 1 times x is the same as just x, so the 5 has been removed. Okay, so that's important. It still holds if I have something like this, x equals 3. If I were to manipulate this by, say, adding something, let's say add 2 to both sides. Let's multiply both sides by 3. Now, if I multiply both sides by 3, I'll have to multiply the entire side. Okay, the entire side, everything gets multiplied. I can rewrite this as 3 times x plus 2 is equal to 15. Maybe I want to subtract something from both sides or add the opposite. Maybe I want to add negative 5. 15 plus a negative 5 or minus 5 is 10. And this is still a true statement. Even though I have this variable x, I know from this first step that x is equal to 3. Well, if I plug 3 in here, 3 plus 2, using order of operations, is 5. 5 times 3 is 15. 15 minus 5 is 10, just what I have here. I could have even, added a step and instead of multiplied by 3, I could have squared both sides. So if I turn this into a square here, well, this is going to turn into a 25, 5 times 5. This turns into a square. I need to then multiply by 3. So if I multiply by 3, that turns into 75. So let's add that 3. This turns into a 75. And then let's say I subtract that 5, I have 70. Okay, so let's see. If I add 3 here, 3 plus 2 is 5 squared, 25 times 3, 75 minus 5, 70. Okay, so we see manipulation so long as you do it to both sides, totally legal with equations, with an equality symbol. Equations means balance. Do the same thing to both sides to keep the balance, okay? And what we are going to work on now is taking this right here, though it's very messy, taking this and solving it. Now, we're not going to worry about the exponents so much, so let's maybe go back to the, we were at 10, the first version. I could actually just undo. Yep, 10. And what we want to do confidently and without any mistakes today, even though you've done this since, some of you 8th grade year, some of you 9th grade year, we have started with something like this, and we figured out, without knowing this, we figured out that the unknown variable must be a 3. We've figured out what this unknown is. Okay, we've solved essentially an equation. Now, here's a very simple one variable equation, 3x minus 2 equals 7. Now, I'll tell you right now, if you can just look at this and get the answer, it's like, oh, well, what minus 2 equals 7? 9 minus 2 equals 7. If you could just say, oh, the answer is 3, great. You could do that. Perfect. If it's easy enough where you can just kind of do the number puzzle in your head, fantastic. I encourage that. Go ahead. But what we will find is that some of the number puzzles will be trickier than others. If I have this number puzzle and I ask you, hey, without doing any kind of algebra, what is the solution for x here? What number can I place in for x so that we have a balance on both sides? And you might think about it long and hard, and some of you might be able to get it, some of you might not. In this one, the answer is 3. Okay, but all of a sudden, doing a number puzzle becomes a very time-consuming process. And if I looked at this guy, and I ask you what value is our unknown, x, so that the left side is equal to the right side, well, you're going to spend a lot of time trying to figure this out. So great, it's good to be able to do some mental calculations and to get an answer quickly, and I want you to encourage you, if you ever get down to something simple like this and go straight to the answer, that's totally fine. But we're going to need to know how to manipulate some things using some rules of algebra, using addition and subtraction and multiplication. How can I simplify this so that I take what starts out like this and remove some of these steps like I did in the opposite direction to end up here? So how can I start here and go this direction so that I get our answer, oh, x has to be 3 for this to be a balanced equation? And to do that, we will undo the order of operations, PEMDAS. Before we do that, let's do quickly a problem you'll see on your homework or on your quiz where you start with an equation. They do not ask you to just undo things and just to arrive at your answer. Instead, they give you options. So I'm just doing this problem just so that you know when you see this on a quiz or on a homework. If you see this question, do not solve. Instead, here are some options. Are these the solutions? The only way we can see if they are solutions is to check. I can plug in -2, and let's see if m is equal to -2. And whenever I substitute in, we want to use parentheses. I'm going to get rid of this subtraction, add the opposite. Positive times a negative is a negative. Negative times a negative is a positive. Again, -13 is equal to 11. This is not a true statement. This is not a balanced equation. So m equals -2 is not the correct answer. Let's try m equals 1. So if I used 1, I get 5 minus 3, which is 2, and 3 plus 5, or -3 plus 5, that's 2. So that gives me something that is true and is balanced. So it turns out, boom, that's our solution. Without doing any algebra, without kind of backing things out, I can kind of arrive at my answer. And I should probably check 3. I plugged in 3, 5 times 3 minus 3 equals -3 times 3 plus 5. Change that into a plus and negative. I have 15 plus -3 equals -9 plus 5. This is 12, and this is -4. So not true. That just confirms my only solution is 1. Okay, if you see a question like that, similar to kind of like these number puzzles here, if you didn't want to use algebra to find our solutions, well, you could just start guessing and checking and plugging in values and see if you got close. However, you're going to find that's going to take you a long time. Instead, what we can use are our properties of algebra, our properties of addition, our properties of subtraction, our properties of adding the opposite to get a 0, property of multiplying by the reciprocal to get a 1, to end up with what our unknown value is without kind of guessing and checking, okay? And what we are doing is undoing the order of operations, which is PEMDAS. So if I rewrote PEMDAS, our order of operations, in the opposite direction, it'd be SADMEP. What is done to our variable is in this order. To undo what is being done to our variable, we can just do the opposite of our order of operations. We can use SADMEP, used to undo what is being done. Okay, which means the last thing that happened to our variable was adding and subtracting something. We see our variable here. We want to understand what that value is. We want to kind of unlock its hidden value. Well, the last thing that was done to this variable after it was multiplied by 3 was it was added 1. Okay, I started with a value. It appears that I multiplied both sides by 3, and then I added 1. Let's get rid of the 1, and I'll undo what 1 does to the 3x. Now, to get rid of the 1, I want to make it a 0. Well, add the opposite. Now it's an equation. We have this side of the equation, we have that side of the equation. Make sure we do it to both sides of the equation. Now I'm adding -1. It looks like just under 1, but I'm actually adding it to like the entire side. However, with addition, you don't distribute with addition. Okay? It is just -1 plus 3x plus 1. I have like terms of the -1 and the 1. Those can be combined to create a 0, giving us a 3x plus 0. I don't want to write the plus 0 because it's not necessary. It's just the same as 3x. But on the right side, I've added -1 to 7, and I get a 6. Okay? Well, let's undo what the 3 is doing to the x. The 3 is multiplying by x. To undo a 3, to make it a 1, I can multiply by 1/3. This is the same as dividing by 3. I don't care if you have already solve this and you divided by 3, I don't care. It's the same as multiplying by 1/3. I multiply by 1/3. You can multiply by 3, or sorry, you can divide by 3. It's the same, but what we have done is turn this 1/3 times 3 into a 1. 1 times x is equal to 6 times 1/3, which is just going to be 2. And I've discovered the hidden value 2 that will have this equation be balanced. If I plug in 2, 3 times 2 plus 1, that's 7. That is a way for me to just mentally check to make sure that I got the right answer. I'm not going to force you to check your answers, but I would like you to look back and mentally check just by saying, okay, if x is 2, does that work? Well, 3 times 2 is 6, plus 1 is 7, it does. We will ramp up the difficulty pretty quickly in this class. Yes, we are reviewing, but we'll see that we're going straight into distribution and then variables on both sides, and then we have fractions, decimals. So this is why this is a review, and I do feel comfortable going quickly through this stuff. So here we have 3x plus 2 is equal to 12. There's actually a lot of things that can be done here. And what's important in algebra is I'm not going to tell you one specific way to get the right answer. As long as you are using the tools of equality, keeping things balanced, and then making sure you're not making mistakes with addition and subtraction and multiplication and division. This is a great example of a problem that can be solved multiple ways. And I want you to encourage, do whatever is comfortable with you. Sure, what's comfortable for you, but also try something different. You know, don't just say, this is how I've always done this. I'm going to continue to do it this way. Most of you probably, if you're already started this problem, have distributed this 3. And you said, okay, well, I want to get rid of those parentheses. And I have 3x plus 6, sorry. Is equal to 12. And then you're like, okay, I want to undo the addition and the subtraction. That was the last thing that was done to the 3x. I will then add the opposite or subtract. And then I get 3x is equal to positive 6. And the last thing I can do is multiply by the reciprocal to get rid of the 3 and make it a 1. And I get x is equal to 2. Great. If you did it that way, fantastic. You got the right answer. But watch how I can do a different way to get the same exact answer. And this is just through inspection of what I have. 3 times x plus 2. Why don't I just multiply this entire side by a third? Why not just get rid of this 3 first? 3 times a third. Now, you think, oh, well, don't I have distribution? Don't I have to distribute this everywhere? Well, if you wanted to rewrite it, it's 1/3 times 3 times x plus 2. You can multiply things in any order. And I'm going to multiply the 3 and the 1/3 first, giving me just a 1 and leaving x plus 2. Okay, I do not have to distribute things. This is this times this times this. I can multiply a and b first together before I multiply by c. So that just leaves me a 1 times x plus 2. Over here on the right side, at 12 times a third, that's 12 over 1 times 1 over 3, or 12 over 3, which is just 4. And look, I have this simple equation, x plus 2 is equal to 4. I can get rid of this 2 by adding the opposite to create a 0. This turns into x plus 0, which again is just x. So it's not necessary, and that's equal to 2. Boom! Bet you very few of you decided to divide by 3 right off the bat. If you did, great. Also, just letting you know, the videos are not going to be as direct as these are. This is my first time teaching this specific college algebra class, so I don't have videos of lessons from the past like I do in my calculus classes, which is I've taught for many years in a row. So most of the videos that I will be recording that you can use will be actual class videos where I'm providing probably more time in between problems, and I'm asking questions, and you guys are answering questions as a group. So just know that. All right, here's another type of equation. We have lots of variables. We haven't seen this before, but I have variables on both sides of the equations and multiple variables on both sides of the equations. What do I do here? There's a lot of things you can do. The important thing to know is that you may simplify on one side as long as you are not changing the side by adding without adding on the other side. Okay, simplification on the side is totally fine. So like we have like terms, 5 and then 2x. Well, this is a plus a negative 2x. I can combine that 5x and that negative 2x. That's 3x's. If I have other terms, like the 2 and the 3, these are like terms. I can add those two together. That's 5. Notice I changed that to plus a minus. That helps me tremendously, knowing that it's not like minus a 7x or something like that. Okay? Get rid of your subtraction symbols. They only cause confusion to lots of students. Over here on the right side, I can simplify the right side. I can combine some like terms. 7x and a negative x, that gives me a 6x. 2 plus a 5, that gives me a 7. Okay, now I have a situation where I have variables still on both sides, but at least I don't have multiple sets of variables. What do I do now? Well, I want to isolate my variable so that I just have it by itself. Well, I can't have it by itself if it's in two locations. And I can't simplify these 3x's and these 6x's like I did here because they're on opposite sides of the equation. So this is when we are going to want to remove them from one side so that they remain on the other side. And it doesn't matter which side you decide to remove them on. Let's say I like to work with just positive x's for the most part. Let's remove these 3x's by adding the opposite, but make sure you do it to both sides. Now, 3x plus negative 3x, I have 0 x's over here, which is just 0. So I just have 5 left over. But the 6x plus the negative 3x is 3x's. All of a sudden, I have simplified things so that I have just x's on one side. I only have x's in one location right there. That's good. I can now, rescue this x, save it by getting rid of the 7 and then the 3. The 7, which is being added last, and then the 3, which is being multiplied, which can be gotten rid of before that or after that. So I'm going to add a negative 7 to create a 0, giving me, and make sure I do it on both sides, giving me negative 2 is equal to 3x plus 0, which is just 0. Now I need to get rid of this 3. The 3 is bothering the x. I want to remove it. I want to get it by itself, the x by itself. I will multiply both sides by 1/3, giving me x is equal to, now I have negative 2 times 1/3. That cannot be simplified. That just ends up being negative 2/3. Okay, so that's how we deal with multiple variables on multiple sides. We do this key step, which is to get rid of them on one side so that they remain on the other side. Notice my answer. I have the x on the right side. X is equal to negative 2/3. Totally fine. Leave it like that. That's just it's showing you what your unknown value is. Okay? Doesn't matter which side you have your x's on, whether it's the right or the left. I like math to be, lingual in both the left and right directions and the right to left directions. So, which is why I like to use addition rather than subtraction, because subtraction only works from left to right. Here's another example. Here we have x's on both sides, and we have parentheses, which means we must kind of distribute. We can do a lot of things if we wanted to. We could try to divide everything by 2, just off the bat, maybe to make this 4 a 2 and the 6 a 3, this 2 a 1. But this would make this, 1/2 in front of this. So maybe dividing straight off the bat is not a good idea. Instead, it's best to try to simplify as much as possible and to get rid of the parentheses using simplification and distribution. First thing I'm going to do is make sure I notice the subtraction symbols. Subtraction symbols I don't like. I'm changing them to add the opposite. This subtraction symbol I'm going to change into add the opposite. Okay? Now we'll come back to what this opposite before parentheses means. But now, since I can't simplify what's inside the parentheses because it has x's in it and I don't know what it is, I need to distribute this 4 and this -6 so that those parentheses go away. So I multiply 4 by x, I get 4x. Multiply 4 by 2, I get 8. Here, I'll get -6x and I'll get -18. On the right side, I'll do the same thing. 2 times x and 2 times 1. But here it's like, what do I distribute? Do I distribute the negative? Sure. Think of it as like a -1. If I have 1 times 2x plus 1, like this, still just 2x plus 1. It's not changing it. But now that 1 is a negative. And you can distribute this -1. Notice, because I got rid of the subtraction symbols, I only have addition. This is great. Only having addition is good practices. It will prevent mistakes. Get rid of subtraction, change it to add the opposite. Now I have 4x and -6, which are like terms. We can simplify on both sides. Now notice, I'm not going to add 6x and 6x like that. This is a common mistake made for students that don't have strong algebra fundamentals. Now I'm going to pause. I've been talking a lot. I need to take a drink of water. So I want you guys, and in this class, and I'll spend more time on this, like in the Genius Hour as well. In this class, you are going to use the students sitting around you to help answer questions and to help check work. Typically, whenever I ask a question to the class, I'd like everybody to discuss the answers so that everybody has a chance to kind of think through and to talk with their fellow students over what they think the answer is, rather than like whoever's thinking the quickest or whoever has the most confidence raises their hand and they answer. So here's an example of this. Okay, I'm asking the class. However, when I ask the class, I want you to discuss this with your neighbors. Okay, I would like you right now to discuss why you cannot do this in this equation at this step, at this moment in time. Please discuss with your neighbors why that's bad. Ready, set, go. I know you're probably uncomfortable right now because it's like just a sub sitting on the side, and you're like, gosh, what are we doing here? This is the first day of class and my teacher's not even here. Don't care. You're going to get used to it, and I'm going to see you on Monday. This is how we do things. You're going to discuss with your neighbors why answers to my own questions. So here's an example. Ready, set, go. Hopefully on the first day of class, I had you introduce yourself to the neighbors. That's usually something that I do. If not, we're going to learn more about our neighbors during the Genius Hour. All right, fantastic. Stop talking about the stuff that doesn't involve the question. Instead, let's talk about the answer, the actual answer to why we can't do this. Why couldn't I just add 6x and 6x to get rid of this? It's because of the equation. You are adding a total of 12 x's to one side of the equation, whereas you are not adding anything to the other side of the equation. You are unbalancing the equation by doing this. This is bad. Okay, this is a reason why you can't do this. If you were to add 6x and 6x, you got to add it on both sides. Now all of a sudden things are okay. These can go away. This turns into 10x's. And over here on this side, this can turn into 12x's plus 2x's, which is 14 minus 2, which is 12x's. So sure, if you'd like to do that, that's fine. But I wouldn't want to do that. Instead, what I would want to do is just to combine. Same side, combine. Okay? What's 4x plus negative 6x? Negative 2x. What is 8 plus negative 18? I got more negatives here, so I'm going to be essentially like taking away negatives by adding those positives. That gives me negative 10. On the right side, this 2x and this 2x, like terms. Same side, combine. 2x minus 2x, or 2x plus negative 2x, 0 x's. I also have 2 and negative 1, or 2 plus negative 1. Same side, combine. 2 plus negative 1 is 1. So this is just 1. Okay? We are ready to then solve. I want to get x by itself. What do I need to do? Remove the negative 10 that was done last to it. So I'm going to remove it first. Add the opposite. And then I'm going to multiply by the reciprocal. I'm going to keep the same sign. That creates a 1. Negative 2 times negative 1/2 is just 1. And this becomes negative 11 halves. Okay? So remember, same side combined. Do not add multiple x's onto one side of the equation. Things are unbalanced. Dealing with fractions. Multiple ways to deal with fractions. Multiple ways to deal with this specific equation. Let me just show you, two possible ways. So I'll rewrite it here. All right, first way. Let's say I see that I can't simplify anything. I see I have y's on both sides of the equation, and I want to get y's all on one side of the equation. Okay, so I want to combine my y's. Well, since they are on opposite sides of an equation, I'm going to add the opposite of one of them so that they return to the other side. Now, this is a good example of, just be careful while you're working. Make sure you know where the equal sign is. Here, the y over 3 plus the negative y over 3 does turn it into a 0. And in this situation, I do want the 0 to be written down because we have nothing left on this right side, but we need to make sure that is shown. Now I have negative 14/15, but now I have a little side problem here. How can I add 4y over 5 to negative y over 3? This is when we're going to need to use our like terms. Okay, we want a common denominator so that they are like terms. Well, if you can't figure out like the common denominator or a common multiple of 5 and 3, easiest thing to do is just to multiply by the opposite, the other one. Okay, now remember, I can't just multiply the bottom by 3 and this bottom by 5. I have to multiply the top and bottom because it's a version of 1. Okay, this turns into 12y over 15. And this turns into negative 5y, and I'm adding this, not equals to, over 15. They are like terms. They are y over 15s. I have 12 of them, and I'm adding negative 5. That gives me 7 y's over 15. Okay, so this is 7y over 15 plus negative 14 over 15. Okay, so that was a little side problem. And I can now remove what is being added to the y, the 14 over 15. I'm going to add the opposite, so positive Notice I needed that 0 here so that I know I still have an equal sign. 7y over 15 equals 14 over 15. Now, we got to get rid of the 15 and the 7, which is bothering my y. I need to get it by itself. What should I do? Well, you can do multiple things. You can get rid of the 15 first by multiplying by 15. It undoes the division of 15. And then get rid of the 7 by dividing or multiplying by 1/7. Or you could think of this as 7 over 15 times y. That is a simpler method of 7y over 15. 7/15 times y. How do I get rid of something being multiplied? Multiply it by the reciprocal. I can multiply both sides by 15 over 7. Multiply this side by 15 over 7. Okay? Now, why does that work? Because the 15 divided by the 15 is a 1. The 7 divided by the 7, or the 7 times 1/7, is a 1. That leaves us with just y. Sorry about that. Technical difficulties. So I just have y. And over here, again, if you'd like to, you can rewrite this as 14 times 1/15 times 15 times 1/7. You can do this multiplication in any order. The 15 times the 1/15 is just a 1. 14 times 1/7, or 14 divided by 7, is just 2. Okay? That's just one way to do that. Okay? What's another way to do it? I actually can decide to simplify so that I don't have fractions off the bat. Now, let's see. 5 and 3 are all factors of 15. If I decide to just multiply both sides of this equation by 15, watch what happens. All right, so I distribute the 15 times 4y over 5 turns into 3 times 4y, which is just 12y. 15 times a negative 14 over 15 is just negative 14. And y over 3 times 15, that's like y times 1/3 times 15. 15 times 1/3 is the same as 15 divided by 3. That's just 5. That's just 5y. All of a sudden, I don't have to deal with fractions anymore. I just decided to start out by simplifying things by multiplying. Now I can, let's say I want to move the y's onto the right side. I can add the negative 12y's from both sides. I have negative 14 is equal to negative 12 plus 5 ends up being negative 7. And how do I get rid of the negative 7? Multiply by the reciprocal or divide by negative 1/7. Divide by 7, negative 7. And there you go, you get that y equals 2. Okay, so algebra, many ways to do the same thing. Probably in this situation, if you're working ahead, but I'm going to quickly do the next couple. What's my time? Yep, gotta quickly move here. In this situation, I'd probably combine. I'd probably subtract the y over 4s or subtract the y over 10s rather than multiplying everything, because if I multiplied everything, it'd get a little bit messy and the numbers would grow. So I'm just going to combine these. Now, what's a common multiple of 4 and 10 is 20. To make 20, I need to multiply this by 5 over 5 and this by 2 over 2. So this gives me 5y over 20 plus negative 2y over 20. This turns into 3y's over 20. Okay, so that was a little side problem here. I have 6 is equal to 3y over 20 plus 12. Can subtract 12, I get negative 6, or add negative 12 to both sides. Sorry for speeding up. And now I can get rid of this 3 over 20 by multiplying by 20 and divided by 3 all at once. Again, instead of kind of treating this as just one fraction, I can split this into multiple parts. I can think of this as like 20 times 1/3 times -6. And that's easier to work with because I can multiply the 1/3 and the -6 first. That becomes -2. And -2 times 20 is -40. Okay, now for all these problems, if I had time, I'd go back and just make sure that works. I'm going to do that really quickly here. Does this work, or did I make a mistake? Well, -40 divided by 10 is going to be -4 plus 6, that's 2. Okay, so that's easy. And here, -40 divided by 4, that is -10 plus 12, that's 2. So that works out really well. 2 equals 2. Easy way to fix that. Let's look at this problem really quickly. 2 ways to do this. I'm just going to show you the introduction of the 2 ways to do this. I'm not going to kind of work through it because we are running out of time. One way is to think of this numerator as being something in parentheses, and instead of dividing by 3, use the multiplicative reciprocal. And say, hey, that's not r plus 2 over 3, that's 1/3 times r plus 2. And this is 1/4 times 3 minus r. And then we can distribute and then combine our like terms and then remove stuff to solve. So that's one way you could do things. Totally valid. Another way is to, again, kind of doing what we did before, is to simplify by multiplying both sides by a specific number. Now, it's going to be best if it's a number that 3 and 4 are both factors of. The number 12 comes to mind because if I distribute the 12 in, it'll be 12 times 1/3, which is just 4, r plus 2, and then 12 times 1/4 is 3, 3 minus r. I don't want that minus r, I'm going to make that a plus a negative r. And we go from there. Really quickly, distributing, combining, same side, combine. Same side, combine. Add the opposite to get rid of and solve. -5 plus 2 is -3. -3 divided by 3 is -1. 3 plus -5 is, or 3 minus -5, that's 3 plus a positive 5, which is 8. 8 divided by 4 is 2. 2 minus 1, boom, hit 1. Okay, similar thing here. I'll leave this problem for you guys to do, and I will do it at the end of class, at the end of the video. So moving on. Let's talk about decimals. Really quickly, we can just deal with decimals, and if you're comfortable adding, subtracting decimals, that's fine. Just a real quick hint. Instead of working with decimals, if you wanted to, just like we did before, multiply both sides by a specific number that simplifies things, that might be a good way to approach this problem. If I multiply by 10, 10 times 0.1, which is 1/10, is just 1. And we just move the decimal place over once, sorry. So I get x plus 3 minus 5x equals 7. This might be a lot easier to work with than with the decimals if you're not comfortable with working with decimals. Again, same side combine, add the opposite to remove. Multiply by the reciprocal to remove stuff that's being multiplied. Okay, here, for these decimals, since it goes to the 100th place, multiply both sides by 100th. And this may be easier to work with than with decimals. This turns into 14x plus 223 is equal to 9x plus 198. Okay? You will be able to use a 4-function calculator in this class to maybe help with the bigger numbers, but this is all something that we can do simply by hand. I'll save the work for this to the end of class. This guy, if you'd like to, you could distribute right away, but again, maybe it's better to multiply by 10 right away to give you 4y plus 3 is equal to 5y minus 4, and then distribute and solve. I will show you the work for this at the end of class. Yeah, a little less than 10 minutes. I'm sure we did not start right on time. To the last problems. Question is, what does this mean? Okay, I'd like you guys to go ahead and simplify on the same side this and this. And let's see what we get. Well, I get 3x plus 11 on the left side, and the right side is already 3x plus 11. Well, usually when we have x's on both sides of an equation, we want to remove them from one side so that they remain on the other side. However, if I do that, I get 0 x's on the left side and 0 x's on the right side, giving me just 11 equals 11, which is a true statement. What does that mean? Discuss with your neighbors. What do you think that means for this equation? See if any of you can get the answer. What do we think? Well, watch what happens. No matter what value I plug in for x, let's say 0. So this is 0 plus 3 plus 0 plus 8 equals 0 plus 11. I get 11 equals 11. Let's say plug in the value 1. 2 plus 3 plus 1 plus 8. So that's 5, 6, 14. 3 plus 11, 14. Good. If I plugged in a negative value, it would work. If I plugged in a decimal, it would work. Hopefully you remember this from back in the day. If we end up with a statement that is true without the reveal of a specific value for x, turns out that x could be anything. That's any number. It's very messy. My penmanship gets better over the course of the year after a summer of not using this slate at all. My penmanship goes bad, but it will improve. But it's never that good. Just letting you know, my penmanship is pretty bad. Any number. Or we could say x exists in the set of all real numbers. This is kind of like an E. It's like a C with a line in the middle. Just means x is an element of. And this R with the extra kind of line to the side of it is the mathematical symbol for any number, any decimal, all real numbers. This is all, any number that does not involve the square root of a negative, okay? Any number. Similar situation happens here. Let's go ahead and distribute. Let's get rid of that negative. I got 3x plus 9 plus negative 6x is equal to 5x plus 5 plus negative 8x. Same side combine. Same side combine. I got x's on both sides. Let's remove them from one side so they just remain from the other, but they both disappear from both sides. I end up with this. What does that mean? This is not true. This is false. What this means is that this is an unbalanced equation to begin with, and there is no value for x that we can plug in so that this becomes balanced. This statement is a contradictory statement to begin with. This just is not true. So what we say is There are no solutions for x. This is a contradiction. The equation is permanently unbalanced. Okay, one other type of problem you're going to see on your homework and your quiz, just so you're aware of. This is a question, find A, not find A such, but find A, the value for A, so that the solution set to the equation ax plus 3 equals 15 is 2. What that means is when x is 2, the equation is balanced. So x equals 2. All it essentially is changing the question from, solve for x to what is A if x is 2. Okay, and you can rewrite this if you'd like to, but it's a simple equation. Moving forward, I will stop showing all the steps, and I'll just say, okay, I'm adding -3 to get to 12, and then I'm multiplying by a half or dividing by 2 to get A equals 6. Okay, that would be the solution there. Here, find the solution set, find A such that the solution set for ax plus 3 equals 2x plus 3 times x plus 1 is the set of all real numbers. So that means x can be anything. Multiple ways to do this. You can just kind of simplify from the get-go, or since x can be anything, plug in anything for x, like 1. If I plugged in 1, this becomes 3 times 2, which is 6. I have A plus 3 is equal to 8. A has to equal 5. That's one way to do it. So you could even use 0, actually. But don't use 0 because that would get rid of A. So we don't want to remove our answer. Other way to do it is just to kind of simplify and see what's going on here. We get ax plus 3 is equal to 2x plus 3x plus 3. This is ax plus 3 is equal to 5x plus 3. And we can see, okay, ax plus 3, 5x plus 3. This is so messy. I'm going to start again. We can see, like, if the solution needs to be all real numbers, well, A has to equal 5, so that we have the same thing on the left and the right side. All right, that probably is close to the end of the class period. So if the bell had already rung, hopefully you stuck it out for an extra minute or so. But right now I'm going to go back and finish those problems that I didn't do, just so that if you're going back and doing these problems, you can see the answers for all of the problems. So let's go here. Yeah, like I could have distributed this, or I could have multiplied both sides by 6. I probably would distribute, because if I multiplied both sides by 6, I have to multiply the 2 by the 6 as well. A lot of people make mistakes with that, but let's just see if I can use fractions and make it easy. This is plus a negative, so this is plus a -2. It's actually not that bad. Same side combined, that goes away. I have 1/3 x minus 2/3 is equal to 3/2 x. I'm going to subtract the 1/3 x. I have -2/3 x is equal to, on the side, 3/2 x plus -1/3 x. Got to multiply by 3 over 3. Got to multiply by 2 over 2. This becomes 9 over 6x plus -2 over 6x. So that's 7/6x. Multiply by 6, divide by 7. I get x is equal to it does not simplify, -12/21, unless I made a mistake. I'm going to just go back and do this problem again a different way. I could plug it in and see if it works, or just try it again. Maybe try it a different way, see if that works. I'm going to go back and do this by multiplying both sides by 6. I got negative 12 21st, right? Something like that, or negative 21st 12, something like that. So you multiply by 6, I get 2 times x minus 2. And over here, I'd get 3 times 3x plus negative 4 plus 12. Okay? You have to multiply both entire sides. So the 6 times the 1/3 gets rid of this. But on here, I have to distribute it to both the 2 and the 1/2. So this is 2x minus 4, or plus a negative 4. And over here, this is 9x plus negative 12 plus 12. So I get 2x plus negative 4 equals 9x after I same side combine the 12s. I then subtract the 2x. Oh, I had 12 21st, right? I could have divided this by 3 and gotten 4/7. Watch. I add negative 2x to move them onto one side. I get negative 4 is equal to 7x. Divide by 7, or multiply by 1/7. I get x is equal to negative 4/7. I'm sure one of these is negative. All right. So if you do that problem by yourself, make sure you get this as the answer. What other problem did I not do? One of the decimal problems. Yeah, I multiplied this by 100. Now I can, I have nothing on the same side to combine, so I'm going to just add the opposite. This is 5x plus 223 is equal to 198. I'm going to add the opposite to get rid of the 223 to try to isolate the x. So 223 minus 198. This turns into 21. This is 13. This is 5. This is 25. So I get 5x is equal to 25. Divide both sides by 5. Multiply both sides by 1/5. Same thing. X is 5. This guy multiplied by 10. I'm set up to distribute. Easier than to try to divide by or multiply by anything. Sorry, this is 4y plus 12 is equal to 5y minus 20. I'm going to go ahead and remove these so that I had positive y's on the right side. If I wanted to go ahead and just add the 20 as well to kind of kill two birds, one stone, I have 32 is equal to y. All right, and that's it. So this is all review. Hopefully this was just an easy first day. I know there's a lot of notes, but hopefully we did not struggle with it. If you have any problems, I'll be in Monday morning for you guys to go over any homework questions, or if you have any overall questions or any practice questions, please come in. I'll be in at 7:45 Monday morning. Thank you.